The transaminations involving alanine and glutamate basically are a bridge between anabolic and catabolic processes. Think of it as a way of removing the alpha amino group from alanine to form pyruvate. Or you can visualize it as a way of synthesizing alanine from a glycolytic intermediate. Both of these functions will occur depending upon the metabolic status or needs of the cell. This also highlights the important role of glutamate as a source of alpha amino nitrogens. Glutamate can be formed from alpha ketoglutarate and ammonia. It can then go on to donate the alpha amino group to form any of the other 19 amino acids in transamination reaction. In this slide, we see that the carbon chains of asparagine and aspartate can enter the citric acid cycle by the formation of oxaloacetate. Asparagine can be converted to aspartate in a reaction catalyzed by asparaginase. The amide group of asparagine is removed as an ammonium ion, as we see here. That ammonium ion can enter the urea cycle or be converted to an organic nitrogen by glutamate dehydrogenase. The ammonium ion and alpha ketoglutarate, in this case, plus NADPH and hydrogen ion can produce glutamate, NADP, and water. The aspartate then can enter the citric acid cycle as oxaloacetate by a transamination reaction, which is occurring here. Here's a parallel example in which the carbon skeletons of two other amide amino acids can enter the citric acid cycle. The amide group of glutamine is removed as the ammonium ion by the action of this enzyme, glutaminase. Again, the ammonium can enter the urea cycle or be converted again to an organic nitrogen. This reaction can also be reversed by glutamine synthetase, not shown here. That glutamate, in turn, can be converted to an alpha ketoglutarate, or it can function as a precursor for a number of other biological molecules or intermediates. So here's an example of a complicated catabolic pathway that you don't need to worry about, but it shows the carbon skeletons of some of our aromatic amino acids, for example, phenylalanine and tyrosine. These are considered to be ketogenic amino acids. They can yield acetyl-CoA or some related intermediate that can't be converted to glucose, versus being glucogenic. These types of molecules yield pyruvate, oxaloacetate, alpha ketoglutarate, or some intermediate that can be converted to glucose. So in this flow chart, phenylalanine can be converted to tyrosine in the first reaction, and then a series of reactions produce in the end fumarate and acetoacetate. Fumarate then could be converted to oxaloacetate and then to pyruvate. It can also enter, that pyruvate could enter gluconeogenesis, and the acetoacetate can also be converted to acetyl-CoA. So this figure just gives an overall view of the catabolic fates of these common amino acids. Those that are in the pink boxes, or purple, whatever color it looks to you, are considered to be gluconeogenic, meaning they can be utilized to produce glucose or glycogen, whereas the boxes, the yellow boxes here, are ketogenic amino acids. They can produce acetyl-CoA and acetoacetyl-CoA. And as you see, we can use all of these amino acids to produce pyruvate. We can use asparagine aspartate, which we've already seen that reaction, to produce oxaloacetate. We've seen fumarate as in the just previous slide, coming from tyrosine and phenylalanine. And you don't need to know what amino acids can be utilized, but know that they are utilized in such a way. So finally, I mentioned that there are a number of metabolic intermediates that are branch points to a number of different metabolic pathways. Acetyl-CoA is one of these. And well, we're not going to take the time to do this right now. We will later draw some flow charts that show these central metabolic intermediates and how they connect to these other pathways. But we are going to look at acetyl-CoA presently. So the pyruvate dehydrogenase complex converts pyruvate to acetyl-CoA. So it can enter the citric acid cycle. We also have citrate synthase, which introduces acetyl-CoA into the citric acid cycle when it condenses with oxaloacetate to produce citrate. We've seen acetyl-CoA, in the last step, utilized in the last step of fatty acid oxidation. Beta-keto-thiolase produces acetyl-CoA in that process. Acetyl-CoA carboxylase converts acetyl-CoA to malonyl-CoA in fatty acid synthesis. We have also the acyl-malonyl ACP condensing protein that acts, or enzyme, that acts on acetyl-CoA. We saw it also in cholesterol synthesis and reacting with HMG-CoA synthetase. And we've also seen it in the catabolism of some amino acids. So we will come back to acetyl-CoA as a central molecule and a branch point in metabolism. But for this discussion right now, that's all we're going to talk about. So, time to move on to our next topic.